cannot find it. Okay, because it's into a zip file. Just 1 second, I copy it. Okay. I wanted to give you an example in Excel, because in Excel you can see the matrix. It's nice. But in Excel, the computation of the eigenvector is a bit difficult. So basically, the Excel file is just serves just to give you an overview of the matrix, a visual overview of the matrix. But it's, my suggestion is to stick on R for developing this exercise. Okay, now I think that the next step is to give to you the USB stick. And let me see if I have another one, because this one is a bit, could be not compatible under Windows. Do you have connection to our Wi-Fi? Yes. So everybody of yours connection. So if you are connected, I think the easiest thing is to download it from my website. And I don't understand why. So you can connect and then can. There must be a reason. Maybe that your network is a little less easy than mine. It seems that everything is set. Or maybe that I forgot to. Let me see. Probably the reason is that I forgot to update the password for my. Give me 1 second. Okay, perfect. Because you need a password problem. So let me show you where. Okay, this is the page. You can find it here. Exercise on pairwise comparison. And it's a zip file where you can find the text, the Excel file, and the R code. And then there is the second exercise in the bottom here. Just take the first one, okay? Perfect. Okay. So, let me now open in our console. Here as it is. And let's remember what are the criteria. These are our criteria. They are 4 criteria, which means that we need to build, in the pairwise comparison, we need to compare the criteria one by one, and we need to build a 4x4 matrix. There is, in the Excel file, there is a matrix that is proposed, which we don't need to adopt. And the matrix that is proposed is, just one second, is this one. We don't need to adopt it. And let us build another one. So, and let's build it in Excel, because in Excel it's easier because we can make reference to, as I said, to a visual matrix, a visualization that is efficient. And the matrix is a diagonal matrix, so we can put a 1, 1, 1, 1 in the diagonal. And what we need to do now is to compare the indicator 2 by 2 indicators. So let's try to do that. And let's make the first comparison between indicator 1 and indicator 2. And let's see what are these indicators. Economical benefit against the impact on the ecosystem. Keep in mind that if you do this evaluation alone, it's just your evaluation which is subjective. In a participatory approach, of course you need to discuss with the stakeholders this comparison, the ranks that we need to do in these comparisons, like we could discuss in this room. So, of course, the discussion on what is the rank, the importance of the economical benefit on the impact on the ecosystem is a complicated discussion, because if you have stakeholders that are, for instance, those that take advantage, economical advantage from the plant, they will tend to be even higher importance to the economical benefit. If you have stakeholders that are like representative of the fishermen, they will tend to protect the ecosystem. And usually, what could we say here? First of all, the economical benefit is important, because if it was not important, we wouldn't consider building an hydropower plant. And of course, we are willing, if we entertain this discussion, to have an impact on the ecosystem. Usually what comes out from a similar discussion is that the economical benefit is more important than the impact on the ecosystem, but not much more. So what we could say is an importance of 3. Okay? So if we give an importance of 3, I will put a 3 here and a 1/3 here. Oops, sorry. Okay, let's try to do that. And then indicator 1, economical benefit against indicator 3. What is indicator 3? I go back to the Word file. Indicator 3 is the impact on the landscape. Well, one may say that the impact on the landscape is not as important as the impact on the ecosystem, and therefore we may give an importance of 5 to the economical benefit against the impact on the landscape, which means 1/5. It's an anti-symmetric matrix when we compare I3 with I1. And then what is the importance of the economical benefit against the last indicator? And the last indicator is impact on the touristic appeal. Let's suppose that we have an important touristic appeal of the river, so we may say that the importance of the economical benefit is not much higher. which means 1/2 for symmetry reasons. Now, the situation so far was quite simple. The comparison was quite simple. Now it becomes a bit more complicated because we have to take into account the previous evaluations. So when we compare the indicator I3, which is let me say again, impact on the landscape, against I2, which is the impact on the ecosystem, what could we say? We determined before that the impact on the landscape is less important than the impact on the ecosystem as a result of the previous comparisons. So I would say that we should put a decimal here, maybe lower than 1, because I3, landscape, is less important than I2, ecosystem. So what could we say? I would say, let's try to put 1/2 here, which means for symmetry reason that we should place a 2 here. Okay, and then we need to compare the impact on the landscape against the impact on the tourism. Again, I will put here, for consistency with the previous evaluation, of 1/3. It's less important, the impact on the landscape, on the tourism with respect to the impact on the ecosystem, because in the previous evaluations we gave to tourism a higher importance with respect to the ecosystem. So let me put 1/3 here, which means 3 here. I'm not sure this matrix is consistent. We need to check it. Now we need a final comparison. The impact on the tourism against the impact on the ecosystem. It's slightly more important, tourism, than the ecosystem. So I will put a 2 here, which means 1/2 here. Is this matrix consistent? I don't know. Let's see. Okay, so this is our matrix, and let's forget about these numbers here, because these numbers refer to the previous matrix that I had. So far we only define the matrix. Now we have to compute the eigenvalues and eigenvector. And just remind that, that the eigenvector x which is the right eigenvector, is defined as in this way. A, the matrix A that we just defined, times x is equal to lambda x, where lambda is the max eigenvalue, which should be close to N. Where N is the dimension of A. Okay, perfect. So I think that now we can move to R. And in order to move to R, the first thing that we have to do is to copy this matrix into R. And how to do that? One possibility would be to copy this matrix to a text file, to a txt file, and upload the txt file into R and create a matrix. This is one possibility. And I would choose this option if the matrix was huge. And in this case, I think we can manually manually insert the matrix into R. I think it's faster. And therefore, let me go to R. What I have to do is, first of all, define a matrix. We can call it X1. It's an array. And let me put into it zeros, and the dimension is equal to 4, 4. So now if I visualize X1, this is my matrix, which is made by zeros. And then let's fill in with the values that we determined in Excel. And in order to fill it, we just have to manually include them. And first of all, I put the diagonal. So 1, 1 is 1, 2, 2 is 1, 3, 3 is 1, and 4, 4 is 1. And now, if I visualize it, I find the ones in the diagonal. Fine. I clean the screen. So I am at this stage, and now I just have to insert manually the other numbers. So let's move forward with 1, 2. And 1, 2, the number is, I go to Excel, is 3. So I have 3, 5, and 2 along this row. So this is 3. 1, 3 is 5. And 1, 4 is 2. Perfect. Okay, now I can move to the second row. 2, 1. 2, 1, I go to Excel to put in memory the numbers 1/3, 1, 2, and 1/2. So this is 1, 2/3. 2, 2, I don't need to include it. Is 2, and 2, 4 is 1. So I just make a check. 1/3, 1, 2, 1/2. I just make a check by going to Excel. Okay, perfect. And now I can move to the third row. So the third row, I go to Excel to memorize it. It's 1/5, 1/2, 1/3. 1/5, 1/2, 1/3. Now I just need the final one, the final row. So I go to Excel to memorize it. It's 1/2, 2, 3. let me show you the matrix. Here it is. Okay. Good. Now let's compute eigenvector and eigenvalues. And I open now the suggested output. And what we have to do now is to use this function eigen. I copied it. I go back to R. So let me define a variable x2, which is given by eigen x1 and symmetric equal false, which means that it's antisymmetric. Now, the result of this function eigen is a list, and we can visualize the structure of a list by asking R what are the names of the elements of the list. And we can see that the elements are the values, so the eigenvalues and the eigenvectors. And keep in mind that these are imaginary numbers, and therefore complex numbers, sorry. These are complex numbers, and therefore we have, in order to convert them to the real numbers that we need to use, we need to compute the module of these complex numbers. This is why in the suggested codes, in order to get the real values of these complex numbers, we use the function, the R function, to compute the module. Basically, if you visualize x2 values, for instance, you see that these are complex numbers. The first one is a real number indeed, but the other are complex. First of all, I see by looking at the first one that is very close to 4, so probably the matrix is consistent. But now, in order to compute the eigenvalues, let's take the module of this complex number. Oh, sorry. And these are the eigenvalues. Which we need to rescale. So let's look at the next one. Sorry, we don't need to rescale these numbers. We need to rescale the elements of the eigenvector that we are computing next. These numbers just serve us because we need to make reference to the highest of them. These are the eigenvalues, and we need to make reference to the highest, because the highest is our lambda, which needs to be close to 4, and indeed it is very close. Now let me compute the eigenvectors, or the eigenvector. And in order to compute the eigenvector, okay, this is the eigenvector. Sorry, again I need to change. So this is the eigenvector, and again I computed these are the modules, and these are the numbers that I need to escape to compute the weights to give to the 4 criteria. So basically, what should I do in order to escape these numbers? I should divide each of them by the sum of the 4 of them. So basically, what I should do is to compute again these numbers, but I should divide them by the sum of them. So the sum of all x2 vectors. And these are the weights. In fact, if you compute the sum of these weights, you can bet that it is 1. No. For some reason, let me see, I made a mistake, so let me see. So I lost my bet first of all, but let me see, because there is a mistake here. Okay, I forgot here the index. Okay, these are the numbers that should sum to 1. Let me bet again. Okay, now it's fine. So basically, these are the weights that I was looking for. I still have to check for consistency. And let me look at these weights. And the first weight refers to the economical benefit. And you may remember that we gave to the economical benefit the higher importance among the 4th criteria, the 4th criteria. And in fact, it got the highest weight. But then you may remember that we gave also importance to the tourism, which is the 4th criteria. And in fact, the weight is 0.27, which means the second weight. And then you may remember that we gave less importance to the ecosystem and the landscape, with the ecosystem more important than the landscape. And in fact, you can see that the weight of the ecosystem is 0.16, while the weight of the landscape is 0.9. So I think that overall it looks consistent what we got. But now we need to check for consistency. And first of all, let me put these weights into a variable. So let me define a variable W1 with the weights. Now we need to check for consistency. And in order to check for consistency, let me refer to the document that I used during my lecture in order to refresh our minds. And also I need to refer to the document because you may remember that there is a table with a coefficient that I need to pick up from a matrix whose dimension is 4. So let me now open the document. Here it is. First of all, I have to compute this quantity, lambda max minus n divided by n minus 1. and let me compute it. I go back to R, and let me see what is lambda max. And lambda max is the maximum of the eigenvalues that we computed before. You may remember it was 4.01. So basically now let me compute this quantity Ci, the Ci is the value, yes, is equal to this quantity here minus 4 divided by 3. And just checking into the document if I applied the formula well, yes. And now I have to divide the Ci by CR for a matrix whose dimension is 4. I go back to the table to pick up this value. The value is 0.9. And I got this value for the consistency index, which is fine, because it's less than 0.1, well less than 0.1. So the matrix is consistent, but now let's play a bit in order to see what happens if we are less thoughtful when we prepare our matrix. Okay, so now let's say that we got to our result. The result is given by this weight under the variable W1, and the weight are 0.48, 0.16, 0.09, 0.27. That's fine. Let's keep them, and now let's play a bit in order to see what happens if we make an inconsistent evaluation. Do you have any question?
Yes, because we have two different results, but until like max mod next to dollar values, we get the same result, but I have 4.03 and you have 4.01. But then the following row, I have a result that is greater than 1 order of magnitude than yours.
So basically, let me say, until when you have the same result, repeat the instruction.
Yes, until max, parenthesis mod, parenthesis x, $2 values. The one before the last one.
Yes.
I have 4.03, I have 4.01. But then the following one, mine, is an order of magnitude greater of yours.
Okay. So I think that the only reason would be, let me show you the matrix first of all. Is it correct? No?
No, there's one number.
Different, yeah. Okay.
Okay, thank you.
No problem. Now let me play with this matrix. And let's assume that we make the last evaluation, which was the evaluation of 4 with respect to 1. Let's assume that we make this final evaluation not consistent. Let me see. No, the final evaluation was with respect to 2. No, it was 4 with respect to 3. Okay, it doesn't matter much. Let's suppose that, let's change in a non-consistent way the evaluation of 4 with respect to 3. So basically 4 is the touristic appeal and 3 is the landscape. You may remember that we gave quite a significant importance to the landscape, and therefore it resulted in an importance of 3 with respect to the touristic appeal, sorry, an importance of 3 with respect to the landscape. Now let's suppose that we make a mistake, and therefore x1 4 3. Let's say that is 1/3, okay, which means that x1 3 4 should be 3, and this is the matrix. This is clearly not consistent what we did, with respect to what we did before. Okay, now let's compute the consistency. And first of all, we need to get the maximum. We need to get this quantity. The problem is that x2, we need to first compute x2. I go back. Here it is, the instruction to compute x2, which is the eigenvalue of